This is my final project presentation for 586. Our problem objective was to design a processor that would handle cryptographic block cipher algorithms. In specific, the IDEA algorithm. Our design needed to be optimized for low latency and for throughput. In order to achieve our low latency and throughput, we're going to look at a few key aspects. First, we're going to look at what we have to build our design with. Then we're going to look at our data dependencies and resource conflicts and how we can optimize those to have a better system. The first choice that I made was to design my system in System Verilog. This allows transparency into my design. Having it in a hardware description language also aids in justifying my design. I can tell whether or not it's cycle accurate. I can go in and see all my signals. In order to handle all cryptographic block algorithms, I decided to make my architecture as broad as possible. I start off with an I-type and R-type instructions, which then I can have an immediate value and an operand for. We'll talk about the special key register a little bit later. That just selects the special key register as one of my operands. I incorporate a load, a store, and then I have my branch instructions, my jump instruction, and then my no op and my halt are basically just a 1-bit flag. We have 14 operations in a round, and we need at least 7 cycles to actually handle those dependencies. And the middle 3 are really problematic. We need the result immediately to create our E prime, F prime, and F double prime. So we're going to need forwarding. We can forward from our EX and MEM stage, and we can have write back and ID be on half cycle so that we can get our results back from write back to be used in ID. Our load dependency can be removed by staggering with our write back to memory. This is my overall design. I have a 5-stage pipeline, and I'm incorporating forwarding paths. I keep all instructions through the stages in the lower bits. In IDEA, I also add the operands for the ALU, and then I have a section to store the data if I'm doing a store. And then in my execute stage, I store the ALU results, and then I replace the operands if I have a load from MEM. We also have to look at registers and resources. We don't have enough registers to save all 52 keys in a traditional system, and if I do create 52 registers just to save keys, then that's a lot of indexing that's going to take away from my instruction set architecture. So I also have to consider the calculation of these and then how many cycles it's going to take me to grab these values and then save them. And then if I don't save them all, then I'm going to have to go back and fetch them again and then be swapping them in and out, and that's going to really not be productive. There's also a key is pretty much standard for most cryptographic block ciphers. So my solution is a special key register. Basically, I overwrite the lower 32 bits on the top so that I can select any 16-bit contiguous key just from an 8-bit input select. This allows me to not have to calculate or do bit shifting. I can just key that into my instruction set and it will automatically grab the right key for me. We have 3 ALUs, but they're not all the same. We only need one complex ALU that is actually capable of doing our modulus multiply, which we have added in special hardware. Because we have less no cycles, our CPI can be calculated from our number of instructions and the number it takes to load the pipeline. Being very close to 1 is wonderful. This, however, is only one piece of our equation. We also need to consider the number of our instructions. I don't have any unnecessary instructions because I have chosen not to do any loops. To calculate our throughput, we need to know our critical path. Appendix C gives us the latency and throughput examples from a modern processor. So I'm going to make some assumptions that my data is like in an L1 cache and that I can grab it in like 6 nanoseconds. My instruction fetch is very small, so I don't really have to worry about that. My write back just needs to access a register which is pretty much the same as my ID stage, but then I have the calculate in my ID stage. And then that's only going to be half a cycle, so I need to multiply that by 2. This brings us to our execute timing. From Appendix C, we find that we can do an integer multiplication in like 4 cycles. That's only 2 nanoseconds. The throughput for very simple integer things is like a quarter of a cycle. So for all of our compares and for our subtracts, we can use this as our estimate. Because we're doing long division by hand and it's all in a combinational cycle, we basically just need to add up all of these parts together. So we add up our introduction into the execute stage, we do our multiply, and then we have possibly 16 different compare and subtract stages because we're doing our modulo multiplication by hand. This definitely gives us our longest stage of 11 nanoseconds. We can then multiply that by our cycles, and we find that we can execute our 1024 bits of data in 21,218 nanoseconds. This allows us to go to our testing. So my first step in testing was to actually get it to compile. Then I wrote a bunch of simple test programs to test the instructions, and these I will include in the submitted materials. Then I wrote the IDEA algorithm in assembly code. I ran it, and it didn't give me the values that I thought it would give me. So I ended up hand doing all of the IDEA algorithm and then testing my values with it just to make sure that my assembly code was actually correct. And I actually found a lot of mistakes in my assembly code and then a lot of mistakes in my hand-done calculations. But by comparing the two together, I was able to step through and complete the entire IDEA algorithm correctly. And here is a short video of me doing that. Alright, here's the assembly code for my IDEA algorithm. We start off by writing in the key and the first 64 bits of data to be encrypted, and then we process our algorithm. They're all 16 64-bit words or 1024 bits of data. Which brings us to instruction 1925, which is our halt instruction. Our data is found at 2000 for our key, and then our first pair, which is from homework 3, so that we can easily verify our IDEA algorithm. We then have the spaces to do the memory write back into of the encrypted data, which we can quickly show in model sim. So we have our data key, and then our first data, and then the solution from homework 3. So our IDEA algorithm is correct and it works. We then can show our special register, which we can do any part select on because we have the extra 32 bits on the top end. We have our general purpose registers, which we 0 is always 0. We copy in the data from memory into 1 and 2. We then use that with the keys to create A, B, C, and D, which we then use to create E, F, E prime, F prime, F double prime, and E double prime, which then we use to create the next values of A, B, C, and D. When we finish all 8.5 rounds, we can use 3 and 4 to hold those values to be written back to memory while we're loading in the new ones, so that we have no gaps in our cycle. We can always look at our memory image as well. So if we scroll back, we can see the spaces where our encrypted data is going to fit. As we scroll forward, we see it being filled in over time. Thank you for watching my video. The only way to improve this would be to go to superscalar or multiple processors. This would allow us to do all of our words concurrently. But this is only an improvement if we're doing more than one word. We can now compare our results with the other IDEA implementations. And we're going to, for that comparison, we will be using transistors and then our throughput. To get an overall transistor count, we basically just sum up all of the components of our system. We have our ALUs, we have our registers, we have our pipeline registers, and then we have some peripheral data. This brings us to approximately 90,000 transistors. For purposes of comparison, we need to convert our throughput to megabits per second. This equals about 47 megabits per second. Our research led us to a comparison of different processors running the IDEA algorithm. We will use this as the basis for our comparison. As you can see, our size is relatively the same, but our megabits per second is double the average. But if we actually take into account the peak, then they definitely win. So in order to actually compete with them, we would need to implement the superscalar or the multiple cores and be doing more than one word in parallel. And here's my bibliography of my references. Thank you for watching my video.